I work for Insilico Medicine. I'm the CEO of the company. We are pretty well known in aging and longevity, and these are my WeChat credentials. So if you are doing any business in China, that's your kind of life and passport, and hopefully people will start building aging clocks using this data. So a few words about the company very briefly. So we were founded in 2014, actually with the support of Deep Knowledge Ventures, Dieter Kaminski here. We are 86 AI scientists now. We are located in 6 countries or regions. We focus on target identification. We focus on design of novel molecules. We also do a lot of work in generative adversarial networks for novel chemistry. And we do most of our work in small molecule design. So that's where we make our money. We try to embrace the MMA principles in drug discovery. So if you want to kind of ping us to a specific point in drug discovery, you won't be able to. So we try to be good in text omics mining, hypothesis generation, small molecule design, and predictions of clinical trials outcomes. We collaborate quite extensively with many academic institutions and small companies. We like working with startups because we help them accelerate their R&D and provide them either with targets or with targets on molecules or just the molecules. We are supported by Juvenescence. Juvenescence, as you know, is a conglomerate now supporting the London Longevity Week, so that's where I came from today. And one of our big supporters is WuXi AppTec, the largest chemical synthesis company in the world. We publish quite extensively, so if you take a picture of the slide, you'll be able to kind of track us back. So unlike many other companies in our space, we like to show at least the directionality of where we're going and some proof of concept. And we rely on massive omics data sets. Currently, we have about 10 million samples harmonized, de-identified, and available for learning. We also have quite a bit of text. I run the pharmacognitive.com. If you go in there, it's about $1.9 trillion worth of government funding that we are tracking for the past 25 years. And now about the aging kind of the story for today's presentation. So as you know, life is unfair, so you work very hard to reach your peak, and afterward it's gradual decline and decay. So we age at every level, from the molecular, cellular, organ systems, even psychological aging is there, and we're working on some of those clocks. So you can eat right, you can exercise, you can diet, you can restrain yourself, you can take some very basic germ protectors, and you can live a little bit longer and a little bit better, but really it's not going to take you all the way like this. But there are a lot of people who are trying and looking at that, and one of the important aspects of today's aging research and major advances in aging research were made in this particular field since 2013, and those are aging clocks. So the first aging clock was actually published by Hannum. It's a group of collaborators, and it's a blood-based methylation aging clock, parametric. Then Horvath kind of established his brand in methylation aging clocks, and his clock is about 2.7 to 3.6 mean absolute error accurate. We published the biochemistry aging clock, the first one using deep learning. It's about 6 years accurate, and we have a patent on the transcriptomic aging clock. It's 4.2 years accurate. We also have multiple other clocks. And if you look at a disease, if you look at many cancers and compare many cancers to each other, you're looking at many pieces of the broken glass. If you are learning on aging, you're looking at a very continuous, slow process. So if you're using deep learning for that, and neural networks for that, they actually learn biology. So they learn the process of breaking before the glass breaks into many pieces. So think of it in biological terms. And there are multiple aging clocks published since 2013. Well, some of the first ones were telomeric aging clocks. It's parametric, we call it shallow. And now there are multiple known, some are unpublished, but known clocks using multiple data types using deep learning. and some of them are using shallow learning. And of course, you can build a clock pretty much using any data type out there. So voice, you can think of yourself as a deep neural net and see if you can guess somebody's age using your sensory organs. A deep learning system can do it better. So we were the first ones to recognize that, and also the age as a feature is probably the most abundant feature. So if your data set looks like Swiss cheese, age is usually there. So you can train a deep neural network on age and get a pretty reasonable accuracy against superhuman. So you can smell aging, you can sense aging, you can tactile feelings, you can touch aging. You can recognize age using voice, video, photo, blood tests, wearable data. Pretty much any data type can be used to predict age. We published quite a bit of papers in this area. Again, the first one was published by us in blood tests. Don't be kind of scared by the first author. No relationship to the actual guy. There are huge numbers of applications for aging clocks in the pharmaceutical industry and also in insurance, in your daily life, in compliance. So if you're selling a pack of cigarettes to somebody on the street using a vending machine, an aging clock is age predictor is a very good thing to have. You can do age-associated, age-adjusted clinical trials enrollment, so adjusting for biological age instead of discriminating by chronological age. You can do age-personalized immunotherapy, immunology, can do health trajectory estimation, mortality predictions, clinical trial outcome prediction, estimating biological relevance of the data type, quality control. So many applications, and what I'm going to talk to you about today as well is the generation of synthetic data. You probably have never heard about the term generative biology. We're currently coining it. So, and as I mentioned, so you can build aging clocks using multiple data types. The question is which one is more valuable. So you can recognize somebody's age very accurately. Very often if somebody looks older than their chronological age, they're sick. If they look younger than their chronological age, maybe they feel a little better. If you look at the value of the genomic data, you can actually not guess your age using a genome unless you have longitudinal sequencing data. So just from the single point, it's very difficult. We are trying, but unless you use epigenetics, it's very difficult to do that. But using a picture, you can do this. And from the picture, you can derive features like age, weight, height, skin health, social status even, right? So if you're dressed in a suit and in a social context, you might guess the wealth of the person as well. So a picture is very often provides more information on the genome. So genomic data is very often overrated. And we put a lot of emphasis on very basic blood tests. So 50, 60 parameters from your recent clinical blood test can be used to predict your age using about 6 years mean absolute error. You can use those aging clocks to kind of deconvolute them into specific features by importance. So you build a vector comprising of all the features going into the deep neural network, and then you randomly shuffle each one and see how each one of those contributes to the accuracy of the predictor. So you can basically rank them by importance. There are many other ways to evaluate the weight of each feature from the deep neural net, so many ways. And here you can see that albumin, glucose, alkaline phosphatase, urea are the most important features when you train on 40 biomarkers from a recent clinical blood test for healthy people. We also did a study like that on about 4 million people. We identified quite a bit of people who were more or less healthy within each population group. For Eastern Europeans, Koreans, and Canadians, trained the deep neural nets using just 20 features from the recent blood test, clinical blood test, and predicted the patient's age. And then we added one feature, so the ethnic group, population group, and built a comprehensive predictor. And then you can test one data set on another data set. So for example, if you test, use Koreans as a test set on a deep neural network trained on Canadians, they look younger to the deep neural net If you test Eastern Europeans on the same Canadian deep neural net, they look older. And that kind of correlates a little bit with life expectancy in the country. And you can see how population-specific the clocks are. You add the population group as a feature, and actually then the clock performs very well on all the populations. One other interesting kind of concept we derived from that particular study is that if you test on NHANES, so large longitudinal data set in the US, if you are predicted to be 5 years or older than your chronological age, your hazard ratio increases. So the probability of dying of any cause increases substantially. If you are predicted to be 5 years or younger than your chronological age, then the probability of dying of any cause decreases. So that's a really cool thing. So you can use it for all kinds of life insurance applications and also clinical trials enrollments. We also did a really cool study where we used age predictors on smokers and non-smokers. Those were self-reported data and also Chantix use in Canada. And noticed that people who smoke, especially in the younger age, they look almost twice as old to the deep neural network trained on non-smokers than non-smokers. And it actually kind of goes down as you age. So maybe people who were more kind of resilient to smoking and to all kinds of stress factors died off. So they look younger to the deep neural network than the people who don't smoke. Actually very interesting for social and behavioral modifications. People who realize that they smoke and they look older to the deep neural network are very often going to consider quitting when they know that they're older. They don't really care if it's healthy or not. Another interesting clock we published is the photo age clock. So here we trained on about 8,500 pictures, high-resolution pictures of German males, 17 to 70. That study was done in collaboration with Beiersdorf. It's a skincare company which is producing Nivea skin cream. And we built a pretty accurate aging clock. So in German males, 17 to 70, on this kind of data set, you get about 2 to 2.3 minutes of error, so very, very accurate aging clock. And you can see the variability of the accuracy by age group. So here we just didn't have as many samples, but also it is much more difficult, becomes much more difficult to predict the age in older adults. Also, you can use multiple techniques. Again, one of the techniques is you remove the part of the face and see how it affects the accuracy of your prediction. So you can use those techniques to evaluate where the most important features are, where the deep neural network is training on. You can see that the corners of the eye actually contribute the most to the accuracy of the prediction. So if you remove like half of the face, remove those corners, yeah, the accuracy of the predictor goes down significantly. So there are many, many tricks you can do with those deep neural networks. So think of it as, you know, if you're doing this on the transcriptome, maybe you're actually going to impact the person's health status. Here, of course, if you're just using plastic surgery and specifically removing those, yes, you will look younger, but you might not necessarily be healthier. And that brings us to the next point. I'll skip a few other clocks because I've got many here, and I don't think I have enough time. But we also have the microbiomic aging clock, which when we published, it was 3.9 years accurate, so using a gut stool sample sequencing data. And now we have the one which is about 5 years accurate, so the accuracy actually decreased a little bit. You can use those clocks again to deconvolute them into important species that make you look younger or older to the deep neural net. And now we kind of switch gears a little bit. I'm out of time, or do I still have? Okay, so another really cool concept that we are developing is that, as I mentioned, you can train on age on very large data sets that do have age, and then use transfer learning to retrain on diseases. So on a much smaller number of data sets. And you can do it on multiple data types, and you can do it across the entire lifespan. And when you do this, you can see what kind of features change when you retrain on diseases, and you can use those features as potential targets for the various age-related diseases. Also, you can use some of those clocks in clinical settings. So some aging clocks can be intervention-relevant clocks. So if you consistently look younger or older than your chronological age once taking a drug or some intervention, and you see that on a population level, then it's an intervention-relevant clock. If people consistently look older or younger than their chronological age when they're sick or when they're in a specific state, that is the disease-relevant aging clock. So we look at both. And this is kind of one of my current projects. So we are training deep neural networks within the age group, within every age group. So let's say 50 to 60, 60 to 70, 70 to 80, to predict the age very, very accurately within the age group. Also looking at the most important features, structuring them into pathways, looking at the transition state change on the pathway level between 50 and 60. Then looking at various causal inference algorithms to understand what is kind of driving the process. And then we're looking at ways to identify new drugs and interventions to make you look younger by specifically targeting those features. You can do it at the cellular level or even at the tissue level. So we already published a couple papers, and we have several programs where we are testing various geroprotectors on cells and also on tissues. And one really cool thing that we kind of are pioneering right now is generative biology. So all of you have heard about deepfakes. So we use this technology for generation of novel molecular structures with desired properties. We can do it with pictures very well. So we do it with other data types, like, for example, transcriptomes and blood tests to expand a data set of, let's say, 100,000 samples to billions. We have a few patents on that. So you basically use age as a generation condition to generate very, very accurate data sets of, let's say, transcriptomic data of specific age. So thank you very much. Again, this is my WeChat, and you can email me. Thank you so much.